Hi, in this video we're going to discuss section 2 of chapter 9 about work and kinetic energy for a single particle. So we're going to think about a single object or a single particle or right, if we have an extended macroscopic object, at least one that we can use our particle model where we can reduce the entire mass and think about it existing as a single point. And that's the only object that we're going to think about in our system and have some ability to have some forces act on that single object coming from an environment. So let's think about work and kinetic energy for this kind of single particle. We can make a simple diagram. For instance, here's that object, single particle here, and we can have some force acting on that particle coming from some external environment. So maybe this is a cart or a book on a table or some other particle in the system, and this is some push or pull coming from, say, a person or some object that we don't define as part of our system. So we consider one particle acted on by, say, a constant force that acts parallel to the direction of motion, pushing or pulling on the particle as it undergoes some displacement, right? So we can imagine this. I have some particle, maybe it has some initial velocity and it's cruising along, and right, therefore it's going to have some associated kinetic energy. And then we could push on that object with some force coming from some external agent from the environment. And we know now that forces lead to acceleration, so if that force acts over some distance, the object is going to be accelerating that entire time, and so the velocity vector is going to increase if that force is aligned with the velocity. We're going to see that we can associate that with a change in the kinetic energy, that the speed of this object increased, and now we can think about the energy of that object increased as well. Notice here that this figure shows an interaction diagram and before and after representations, and this is going to be a very common way that we try to represent problems to think about energy. We're going to think about, what did the system look like initially? What was the initial energy of the system? Because we know that is fixed unless it's acted on by some external agent. And what did the system look like after it evolved over some amount of time? Now, the kinetic energy that we've been describing in this chapter, we can now write down quantitatively. When we talk about the kinetic energy of a massive particle, it's equal to half of the mass of the object times the square of the velocity. Okay. It depends on the particle's mass and the speed, okay, but not on its position, okay, just on its velocity here. Doesn't depend where in the system it is, just depends on the mass and the speed. And notice that it depends on the speed, not the velocity, right? This is a velocity squared, and so this is always positive, and so this is just the scalar component of a velocity squared. Okay. So that means the kinetic energy for a particle that's going with its velocity pointed one direction and the particle with the velocity pointing the other direction, if those two velocities have the same magnitude and those two particles have the same mass, they'll have the same kinetic energy. So kinetic energy is a scalar quantity, right? Notice this is not a vector quantity. Mass is a scalar property. There's just a fixed amount of mass. There's no direction associated with it. And the velocity squared is also a scalar quantity. For the case in which a single constant force then acts on a particle, k changes in direct proportion to the distance traveled. Right, back on the previous slide, we saw that that force that's applied, the further that force acts, right, the longer the distance is over which that force acts, the more acceleration and the more the velocity changes, and thus the more the kinetic energy will change. Our standard units for kinetic energy, we can then read off from this. It's going to be kilograms meters squared per second squared. Okay, this collection of units we give are so common that we give them a name for a famous scientist, Joule, and we call that 1 joule or a joule of energy. So the work done on a single particle system causes the system's kinetic energy to change. Caused its speed to change. Right? The work is coming from that external push and pull. And that work is altering the kinetic energy, and we can just define the work as the change in the kinetic energy for this isolated single particle system. Okay. For the case of a constant force parallel to the direction of motion, the work can be defined as an integral. The formal definition of work is the integral over some path. So S here is some direction in which the force is acting. We can take that force and integrate it over that distance that it's acting. Now in this integral, F is a constant. We're going to imagine it's a fixed force for simplicity here to see how some of this plays out. We can pull that F outside, and when we do this integral, we just get this positional difference. So for a constant force acting in a fixed direction, the work is equal to that force. The force is parallel to the direction of the motion. Okay. That force, that component of the force, parallel direction times the distance traveled gives me the work. Notice that the units are exactly the same here, right? I get the correct units as I saw for kinetic energy. They better be the same because I see kinetic energy. I'm defining the change in the kinetic energy as work, so they have to have the same units here. Well, this is a force, right? We know a force is like a mass times an acceleration. And this is just a distance here. So if I calculate the units out for this, I get exactly my definition of a joule. Now work has a sign associated with it. It can be either positive or negative. Remember, positive work is increasing my system energy. Negative work is taking energy away from the system. Okay. So if the force causes the particle to speed up, then we say the work is done right. The particle speeding up is gaining kinetic energy. It's boosting up the system energy. Negative work is going to slow the single particle down because that's going to remove the kinetic energy from the system. The sign of the work then can be determined by the force direction compared to the displacement of the object. So we just saw the example of a force acting in the same direction as the velocity of my particle, and it's going to increase the magnitude or speed that particle up. And here you can see the force then is aligned with the displacement. I could also turn that around here and say I start with this particle going in another direction. Again, if that force points in the same direction as the velocity, then as that force gets applied, it's going to accelerate, increasing the magnitude of this velocity vector. Again, we can see the force then is aligned with the displacement vector. In both these cases, we see the particle is speeding up. That would be boosting the energy of the system, and so we say that the work is positive here. If I have a particle that's slowing down, how would that happen? I could imagine having a particle that has its velocity pointing in this direction. There's a force pointing anti-parallel to that velocity. That means there's an acceleration pointing against the velocity that's going to slow the object down. And so here you can see the force opposes the displacement. And even if I have that object acting in another direction, the same logic holds, and the object will slow down as long as the force and the displacement point in opposite directions. So work is negative when the force and the displacement point in opposite directions. When is work equal to zero? Work is equal to zero if the particle doesn't move at all, right? If that force doesn't act over a delta S. Okay, that concludes our discussion of Chapter 2, an introductory discussion of work and kinetic energy acting on single particles.